I'm Noah Golwich. I'm going to talk about our paper on sample-efficient proper PAC learning with approximate differential privacy. This is joint work with Badika Z, Ravi Kumar, and Pasan Manarangsi. So in this talk, I'll discuss privacy-preserving machine learning. And this has attracted a lot of attention in recent years, in part because there's a lot of applications of machine learning in which models are trained on sensitive data, such as healthcare records or hospital data. And in such situations, it's important to protect the privacy of the users whom this data corresponds to. And in this talk, I'm going to discuss a theoretical model which models private machine learning, in particular, the private PAC model, which was introduced over a decade ago. And an exciting recent development in the study of private PAC learning is a connection between private learnability and online learnability, as shown in a couple of papers in recent years. In particular, these papers combined to show that private learnability is equivalent to online learnability. And in this talk, I'm going to discuss our paper, which answers a couple open questions from the direction of this, from the paper by Bunlivni Moran, which showed the online learnability implies private learnability direction of this equivalence. So here's an overview of the talk. I'll begin by discussing some background on private PAC learning, and then I'll discuss our main results. So first, I'll introduce what we call the definition of differential privacy. In this setting, there's a collection of individuals, and each individual produces an example, which is a pair xi, yi, where xi is an element of some feature space x, and yi is a label, either 1 or -1. And a collection of n such examples for n individuals is called a data set, which we denote by Sn. So for instance, each example xi could be a collection of attributes corresponding to a patient in a medical study, and the label yi could represent whether or not that patient has cancer. The goal is to come up with a learning algorithm, which is often going to be randomized, and we're going to denote by A, and A takes as input the data set consisting of the data for these patients in the medical study, and it will output, in this case, a classifier, in other words, a function from the data set x to -1, 1, which predicts whether or not cancer is present in any given patient. The main privacy requirement that we want this private learning algorithm to satisfy is that of differential privacy. So formally, an algorithm A is epsilon delta differentially private for positive reals epsilon and delta. If roughly speaking, for all data sets Sn and Sn prime, which are neighboring in the sense that they differ in a single example, the distribution of the output of A on Sn is similar to the distribution of the output of A on Sn prime. Formally, we require that for any event E, the probability that E occurs under the data set Sn is related to the probability that E occurs under the data set Sn prime by a multiplicative factor of e to the epsilon and an additive term of delta. In this talk, you can think of epsilon as being a small constant, for instance, 0.01, and delta as being something which decays faster than any polynomial in n. So that's the definition of differential privacy. Next, I'll discuss the basics of PAC learning. So in this setting, we're given a known class big F of hypotheses, namely binary functions, namely functions from f from x to -1, 1. And we make the assumption the data set Sn is drawn IID from some unknown distribution P on the space X of features across the labels -1, 1. And the goal is as follows. We want the algorithm A, which takes as input Sn, to output a hypothesis F hat, which minimizes the misclassification error on the distribution P. In particular, the probability for an example xy drawn from P that F hat of X is not equal to Y. And in this talk, for simplicity, I'll make the further assumption of realizability. In particular, I'll assume that there exists a hypothesis F star, so that F star correctly classifies all examples in the support of the distribution P. Now, it turns out that for private PAC learning, this is actually without loss of generality, as shown by Alon, by Moran, and Stemmer. In particular, they showed that for any private PAC learning algorithm in the realizable setting, it can be modified with only a small increase in the sample complexity to get a private PAC learning algorithm in the non-realizable setting. particular in the agnostic setting. And finally, I'll define an algorithm A to be proper if the hypothesis F hat that it outputs belongs to class F with probability 1. And algorithms which are not proper are known as improper. Okay, so the private PAC model essentially combines the PAC model and the private model. In particular, we require that the algorithm A, which maps the data set Sn to F hat, is epsilon delta differentially private. And as I mentioned a couple of slides ago, it's known, as we saw in recent years, that those binary hypothesis classes which have a private PAC learning algorithm that can achieve non-trivial error, in other words, error going to 0 as a number of users n goes to infinity, those classes are exactly those classes with finite Littlestone dimension. And now Littlestone dimension will play an important role in this talk, so I'll next define it. To do so, I have to make a couple definitions beforehand. So let's consider a binary tree, all of whose internal nodes are labeled by elements of the feature space X, and whose edges are labeled by -1 and 1. We say that such a tree is shattered by the class F if for each leaf L of the tree, there's some hypothesis FL in the class, which labels each node in the root to leaf path for the leaf L, according to the label coming out of each, the label corresponds to the edge coming out of each respective node in the path. So for instance, for the green leaf, L, we want the hypothesis FL, which maps x1 to -1, x2 1 to 1, and x3 2 to 1. And now the Littlestone dimension of hypothesis class, denoted by LDIM of F, is simply the largest positive integer D, so that there exists a tree of depth D, which is shattered by F. So for instance, this tree here has depth 3. And it's done finding this Littlestone dimension of a hypothesis class F characterizes its online learnability. And that's why these results shown here are showing that private PAC learning is equivalent to online learnability. Basically, the equivalence is through the Littlestone dimension. Okay, so here's a few examples of classes with finite Littlestone dimension. Any finite class F has Littlestone dimension bounded above by the logarithm of the size of the class. And this can be seen simply by noting that the hypothesis corresponding to each leaf of a shattered tree must be distinct, and therefore the number of functions in the class must be at least the number of leaves in a shattered tree. As an example of a class for which this is tight, we can consider the threshold functions on a domain of size 2 to the d. To be clear, there's 2 to the d such threshold functions. One corresponds to each integer from 1 to 2 to the d. And threshold of I evaluates to 1 on a point j if and only if I is at most j. Otherwise, the threshold evaluates to -1. And so clearly the Littlestone dimension of this class by the first bullet point is at most d. To see that it's at least d, we can simply construct the binary search tree for the domain from 1 to 2 to the d. So here is shown the example for d equals 3. And it's straightforward to check that this tree is indeed shattered. For instance, for the green leaf, we want a threshold which evaluates to -1 on 4 and to 1 on 2 and 3. That's the threshold corresponding to 3. And so throughout this talk, I'll use the letter D to denote Littlestone dimension of the class. So next, I'll review some prior works on the sample complexity of PAC learning in both the private and non-private settings. So in the non-private PAC setting, the number of samples n to achieve non-trivial error little of 1, is characterized by the VC dimension of the hypothesis class. This is another combinatorial parameter which characterizes, in this case, non-private PAC learnability. In the private PAC learning setting, however, the bounds are much looser. Alon, Livni, Malliaras, and Moran show that the number of samples to achieve non-trivial error must be at least the iterated logarithm of Littlestone dimension of the hypothesis class. And then Bunn, Livni, and Moran showed that this number of samples grows at most exponentially the Littlestone dimension of the class. Now, a couple notes here. The littlest dimension is always bounded below by the VC dimension, and this gap can be arbitrarily large, so private learning in general can be arbitrarily harder than non-private learning. But even for the task of private learning, the upper and lower bounds are very, very far apart. One question you might ask is, how much can you improve this gap by? In particular, how much, the answer question we'll be asking this talk is, how much can you improve the upper bound by? Well, you can't hope for an upper bound, which is sublinear in the Littlestone dimension for private PAC learning, if you want this upper bound to depend only on the Littlestone dimension. And this is because there exists a hypothesis class, F, whose VC dimension is equal to its Littlestone dimension. And even in the non-private PAC setting, there's a lower bound of VC dimension, which in this case, for this class F, is equal to Littlestone dimension. So you can't hope to get below the Littlestone dimension. And what we show in our paper is that we can actually get basically within a polynomial of the Littlestone dimension. So next, I'll present our main result. So I've shown here just kind of a notation. Remember that F is the hypothesis class and P is a realizable distribution. So what we show is that for a number of samples n, which grows as d to the 6th over epsilon alpha squared, there is an algorithm A, which takes as input n IID samples from the distribution P. The algorithm A is epsilon delta differentially private, and it outputs with high probability a hypothesis F hat, which belongs to class big F. This hypothesis is classification error at most alpha with respect to the distribution P. Now, recall that the fact that F hat is an F means that the algorithm A is proper. Now, our result improves upon that of Bunlin and Ron in two ways. First of all, their sample complexity bound was exponentially larger than ours, and moreover, their learner was not proper. Okay, so next I'll overview the proof of our main result. The first step is to show the existence of an improper private learner with polynomial sample complexity. And this improper private learner has this property that it outputs a hypothesis, which is a special structure that we'll call an SOA hypothesis. This corresponds to a subclass to class F, which in turn satisfies a special property known as K irreducibility. The second step of the proof is to use this property of irreducibility together with a min-max swap, namely applying Sines min-max theorem to upgrade the improper learner to a proper one. Now, the second step is quite standard. In particular, applying Sines min-max theorem in this sense has been used before in the literature on differential privacy. So I'm mostly focused on the first step, but I will note that the notion of irreducibility plays a central role in both of these steps. And so that's what I'll introduce next. So we say that a hypothesis class G, consisting of binary hypotheses, is one irreducible if for any point little x, there's some bit b, so that the Littlestone dimension of the set of hypotheses in G, which map x to b, is equal to the Littlestone dimension of G. In other words, restricting that the hypotheses in G map x to b does not decrease the Littlestone dimension of the class. Now, for positive integers k irreducibility generalizes one irreducibility, essentially by replacing the signal point x with a tree of points of depth k. And now the main idea behind irreducibility is that the SOA hypothesis, which I'll define shortly, corresponding to irreducible classes, has certain stability properties which are conducive to the SOA hypothesis being private. And so what this means is that we can kind of output an SOA hypothesis, and outputting that will be private under certain assumptions, which we'll verify. Okay, so now we'll define SOA hypotheses. For class G and a bit B, as well as a point X, we're going to define the restriction of G to XB to be the set of hypotheses little g in the class big G, which map X to B. And now the SOA hypothesis for class G, denoted by SOA G, which is a mapping from X to -1, 1, is the following function. Given a point X, it outputs whichever bit 1 or -1, such that the restriction of G 2x in that bit has larger Littlestone dimension. And we'll break ties arbitrarily in favor of the bit 1. So that's shown right here in notation. Now it helps to work out an example for SOA hypotheses. So let's consider, for instance, the class of point functions on a set X consisting of 5 points. There's 5 point functions, and the truth table is shown here. Hypothesis GI evaluates to 1 on xj if and only if I is equal to j. And now the SOA hypothesis of this class is shown on the right. And as you can see, it evaluates to -1 identically. So to see why this is the case, first of all, I'll note that the class of point functions G in this setting is actually irreducible. This is because its Littlestone dimension is 1. And for any point x, the Littlestone dimension of the restriction of G to x minus 1 is also equal to 1. And moreover, we'll note that the Littlestone dimension, the restriction of G to x1 is equal to 0 for all x. And so what this means is choosing the label -1 maximizes Littlestone dimension restriction. In other words, SOA G of x is -1 for all x. So one way to think of this SOA hypothesis is it maps each x to whichever label is such that restricting to the point x in that label makes the class larger when it's measured by Littlestone dimension. Okay, so now I can introduce the main kind of stability property of SOAs. And it's the following lemma. Suppose that we have classes H and G, where H is a subset of G. Their Littlestone dimensions are equal, and H is 1 and irreducible. Then we can show that the SOA hypotheses of the classes G and H are identically equal. In other words, they're equal for at all points x. Now, the proof of this lemma is very, very simple, but it turns out we can use it in a fairly powerful way, which I'll next discuss. So first, we're going to take the entire data set of size n. We're going to split it into m disjoint data sets Sn naught of size n naught. And here m and n naught are integers whose product is equal to n. And then, so I'm going to notate those m disjoint data sets as Sn naught 1 through Sn naught m. And for each of these data sets, say for Sn naught 1, we're going to produce a collection of J SOA hypotheses. In particular, they correspond to subclasses G hat 1, 1 through G hat J1. And we'll do the same for all of the M data sets. And the way we produce these G hat IJ is a way such that the following holds. We show that there exists a subclass H star of F, which depends only on the distribution P. So we don't know H star, but in particular does not depend on the data set. It satisfies the following property. For many integers I between 1 and m, there's some J, so that the pair H star G hat Ji satisfies the conditions required of H and G in this lemma. In particular, what the lemma guarantees is that the SOA hypotheses for H star as well as G hat IJ are identically equal. And this turns out to be enough to establish private learnability. In particular, we can use a private sparse selection protocol by Ghazi Kumar and Manurangsi, which is essentially can be viewed as a generalization of the private stable histograms protocol of Beimel the Siemens Stemmer from 2016. And basically using this private sparse selection protocol in combination with the consequence of the SOA stability lemma allows us to output the hypothesis SOA H star and guarantee that it is epsilon delta differentially private. Now, there's many details that I've kind of overlooked here, and you can see the full proof in our paper. Okay, so finally, I'll discuss some implications of our result for the problem of sanitization. I'll begin by introducing this. So sanitization, also known as private query release, is the following problem. We want to give an estimate for the mean of each binary hypothesis class for a given data set. So an example is, let's suppose that we have a data set consisting of data for a bunch of patients in a medical study. Then a sanitizer might output privately statistics of the following form. For instance, 2/3 of the data set is a smoker, 1/3 of the data set is a smoker with cancer, and so on. And so here's the formal definition of sanitizer. For fixed X and F, we say that an algorithm A is a sanitizer for the class F with accuracy alpha and sample complexity n. First of all, it's epsilon delta differentially private. And second, for all data sets S, note that there's no distributional assumption here. The output of A on S is a function est, which maps from F to the real interval -1, 1. So that with high probability for all hypotheses F, est of F is an alpha additive approximation to the mean of F on the data set. Now, sanitization has been studied before, and an important result by Bousquet, Livni, and Ron is that if a class has a private proper learning algorithm, then it has a sanitizer. And now our result shows that if you have finite Littlestone dimension, then the class is a private proper learning algorithm. So we can essentially put these two results together and show the following. If a class F is finite Littlestone dimension equal to D, and dual Littlestone dimension equal to D star, then for a number of samples, which is polynomial in the Littlestone dimension and the dual Littlestone dimension, this class has a sanitizer with sample complexity n, that number of samples, and accuracy alpha. So the dual Littlestone dimension D star is simply the Littlestone dimension of the dual class of F. And it can be shown that D star is always bounded above by its double exponential in D. So in particular, D star is finite if and only if D is finite. And what this means is that we get the following further corollary, that a class F is sanitizable if and only if it is finite Littlestone dimension. The if direction of this is a consequence of our previous corollary and the equivalence of finiteness of Littlestone and dual Littlestone dimensions. And the only if direction this corollary was shown several years ago. Okay, so that concludes our results. I'll next discuss some open questions. The main question is to characterize the sample complexity of both proper and improper private learning up to ideally a constant factor. And this would mirror several other characterization results in the literature for other learning models. For instance, it's known that VC dimension gives such a characterization for non-private PAC learning. Littlestone dimension does so for online learning, and one-way public coin communication complexity of a certain does so for PAC learning with pure differential privacy. And this seems to be a pretty hard question, but there's some natural intermediate questions that one can ask. For instance, can we get a number of samples which is linear in Littlestone dimension? As I mentioned before, that would be best possible for a bound that only depends on Littlestone dimension. However, one can maybe hope for something a little bit stronger. In light of the fact that alone Livni, Malliaras, and Moran showed that basically the best known lower bound that we have on private PAC learning, which is VC dimension plus the iterated logarithm of the Littlestone dimension. So one might hope that we can get an upper bound which is only polynomially worse than this lower bound. Finally, a natural question is whether the sample complexity of proper private learning with approximate differential privacy can be asymptotically larger than the sample complexity for improper private learning. The answer is yes for pure differential privacy, but it's unknown in the case of approximate DP. That's it. Thank you for listening.